So she would have talked about an electrochemical cell. And I'm going to just pretend you never watched it. Sound good? Okay. An electrochemical cell, if you just think about the name, it's probably something that you can get what from? Electricity or energy, but in the form of electricity from some sort of chemical reaction. So it's literally the flow of electrons from one place to another. In English, whenever we describe electrons moving, we call it electricity. Right? It's a device that can convert energy released by a thermodynamically favored redox reaction to electrical energy, or one that conversely can use electrical energy to drive a thermodynamically unfavored redox reaction. All right, so this part is where your phone is not being charged. So when it's not plugged in, your phone is using an electrochemical cell to produce electricity by a thermodynamically favored reaction. So when it's not plugged in, that's because it's going the direction the electron wants to go. And then this one, this is when at night you have to plug it back in to charge it. We are putting the electricity in to move it in the non-favored direction so that when I want it unplugged, it's ready to come back. Does that make sense? It's genius. Okay, I probably said this before, but the next billion trillionaire person is going to be a battery developer. I'm sure of it. That's where the future is. All right. What? Oh, I get it. Okay, a galvanic or voltaic cell involves a thermodynamically favorable reaction, while electrolytic cells involve a thermodynamically unfavored. So they're slightly different. We put energy into this one. The other one gives electricity out. All right, so an electrochemical cell is a device that can convert energy released by a spontaneous reaction. Now, it keeps saying redox. It has to be a redox reaction because it has to be a reaction where, like, I can separate two things and an electron will flow between them. So reduction and oxidation has to happen. But remember, not every reaction out there involves a transfer of electrons, because some reactions, they just rearrange the way they share them. So it has to be a redox reaction, which we learned about in chapter 4. So like a metal becomes a cation because it lost electrons to a non-metal that became an anion. And in order to lose and gain, there had to be a literal transfer. Right. Next. Or one, and this is the same thing it just said. Wait, am I on the same slide? Yep, I am, huh? Yeah. How come no one said you're on the same slide twice in a row? It looks. Oh, maybe because I didn't have the bottom on the last one. I didn't. That's why. My fault. Okay. Both types of cells contain an anode. You need to know these definitions. An anode is where oxidation occurs, and a cathode is where reduction occurs. These are definitely two vocabulary things that you need to know. For what? I just saw her walking out there. Call her real quick. Does she need the Suburban key? I don't. Maybe. And there might be a ton of implements in the back of the Suburban. Okay. If there is, just throw them in the back of my truck. All right. You may remember, you should remember, oxidation is where there's a loss of electrons. Reduction is where there's a gain. Okay. Okay, I better move closer. I found the boundary.
So reduction in charge produced.
The atom is reduced, which means the atom becomes more negative. All right. Well, whatever. Okay. If you have any of this on the test, which this is pretty common, you'll have to label some things. So this drawing is definitely something that like you should be able to label. Not every single minute part of it, but definitely a few things. So this diagram shows a galvanic cell where magnesium metal is oxidized. That means magnesium is losing electrons. Does that sound like something that would naturally happen? Yes. Oh, right here.
Sorry, you meant card.
Oh, my credit card. That makes more sense.
Sorry.
All right. If we lose that, Yvette will kill me. And she scares me, so don't lose it. All right. So the answer to that is yes, that is a normal process because metals are what? From chapter forever? Losers. So in this process, magnesium's losing. That is a favored process. All right. And is the left half cell. So what we mean here is the cell is this beaker and this setup. You okay with that? All right. Anode is where they lose electrons, right? And one more time, does magnesium want to lose electrons? It does. Now, copper, it wants to lose electrons as well. It's a metal, but the more left on the periodic table, we've learned the more reactive, correct? I guess I should draw it like that way. So magnesium will lose electrons easier. I didn't draw it very well, but copper sandwiched pretty far over to the right there. So this is written in a way that would spontaneously happen. All right, so the left half, this is our anode. Our right half is our cathode. All right, so I can finish it. And copper ions are reduced to copper metal in the right half cell. Copper is used like the Statue of Liberty, the top of lots of capitals. It's used because it's one of the three noble metals. Copper is not very reactive, and that's because it really wants to just stay by itself. Magnesium, we would never build anything out of magnesium. Okay, it oxidizes quickly, and if it ever got hot, you would not want to be around it. All right, the net ionic equation for this reaction is Mg solid plus Cu plus 2 goes to Mg plus 2 plus Cus. Do we remember net ionic reactions? You don't have to write it all out, but we have Mg solid, all right, plus it tells me in here I have, does it say the metal? Well, duh. Plus copper 2 sulfate goes to magnesium sulfate. This would be aqueous. This would be aqueous plus copper solid. So the net ionic, if you remember, the thing that's in aqueous both times, you would get rid of. That's where this half reaction came from. All right, you definitely have to be able to write net ionic equations on your exam. All right, as the reaction occurs, electrons are produced in the oxidation half reaction of Mg goes to Mg plus 2 electrons. Okay, this is the half reaction. That means it gave out 2 electrons. Copper uses those 2 electrons. All right, oxidation, it lost. Reduction, it gained to become solid copper. Okay, here are the things that you need to know. Well, like a ton of stuff. So the anode is where oxidation occurs. The cathode is where reduction occurs. One thing that they'll tell you to remember is red cat. So just think of a red cat. Reduction happens at the cathode. All right, that means, all right, oxidation must happen at the anode. All right, tell your partner which side is gaining the electrons. All right, the copper, right? Which side is losing them? All right, so something you 100% need to know is the direction of the flow of electrons. Which way would it go?
Left or right?
All right, from where you lose them to where you gain them. You must label on one of these pictures that the electrons flow from the anode to the cathode. Now, it isn't always left to right, because they don't always put the anode on the left in every picture. So you have to know, and you have to figure out sometimes which one even is the anode. It won't say the word anode or cathode. You have to look at a table to figure that out. And that's coming up, and that's actually not that hard.
The wire be red filled or?
The red, well, they won't color code the wires. I don't really know why she even did that personally. Yeah,
If this were an electrolytic cell, would everything just be reversed?
yep. We'd have to produce power to get it to go the other way.
So which ones become reversed, which ones don't become reversed?
What do you mean?
Like, just tell us. Like this is
It would use it'd say like copper was used to plate a magnesium strip. All right, sorry, +2. All right, to become magnesium +2 and copper solid. Okay, I'm saying this wrong. Let me draw it out. So they'd say like a penny. A penny is zinc that has copper on the outside of it. They're using electricity to force the copper to stick to the zinc. And it will say like the electrolysis was used. That means I put the electricity in, or electroplating. Those are the 2 things it will tell you. And we're coming up on these. All right. So another thing you need to know. So the flow of electrons is always from anode to cathode. Then we need to talk about this thing called the salt bridge. Nature works in a way where everything sort of balances out, not sort of, where it balances out. If I have negatively charged things moving from here to there, they will only go there if I can stay balanced in my charge. The charges have to stay neutral. So if a minus is coming over here, we have this salt bridge. All right, and it's full of NaCl. It's hard to see, but it's right here. Can you see the NaCl salt bridge? If the electrons are coming this way, then the Na+ ions in the salt bridge will come this direction, and the charges will neutralize.
Is the salt bridge filled with water?
It doesn't have to be water, but some sort of solution, or you don't want direct water. That's why like it's plugged with cotton. So there's like an interaction at a moist surface, but not a direct flow of water, if that makes sense. Or it would just diffuse and the whole system would fail. All right. So the salt bridge, you have to know the direction of ion flow. Okay. And the positive ion, or the cation, goes towards the cathode. The anion goes towards the anode. That's actually one sentence in chemistry that sort of makes sense. That the cation goes towards the cathode and the anion goes towards the anode. You have to explain the importance of a salt bridge. It doesn't have to be a paragraph. It has to just say the salt bridge is required to balance out the charges. Because if this side became negative, why would an electron ever flow to that side? It wouldn't. It has to stay neutral. Now, it doesn't stay positive either. It stays exactly neutral. Okay. So the main things you have to be able to label: which one is the anode, which one is the cathode. You have to label the direction of electron flow. You have to label the direction that the cation would go and the direction the anion would go. You okay with that? You have to be able to explain the importance of a salt bridge. So if you break open like a AA battery, it was almost so good until I failed at that bottom line. I was right there. That was going to be like my peak of my career. All right. It's they call it a copper top, right? That's one of them. So you'd have like Cu and Mg, and then they have like a little cardboard disc that's just a little bit damp, and it's all sealed. This is your salt bridge. All right, and then the electrons don't flow from here to here until we provide an external circuit for that to happen. You okay with that? So you know how they say store your batteries in a refrigerator to help them last longer? You ever heard that before? Okay, well, your parents have. It's to make sure the salt bridge doesn't dry out. Because an unused battery, it doesn't go dead. This goes dry, and then that's technically dead. The ability of an electron to go from here to there still exists, but if this is dry, it can't balance the charge and the battery won't ever work.
So if you have a better, just put it in water or salt.
Cut it in half, drop a few drops of water, weld it back together. Okay, maybe not. But yeah, technically, if you could re-moisten, I don't know, if you could get that to work again, it'd be fine.
What about a recharge battery?
Yeah, the rechargeable battery is just set up in a way that it allows the electrons to flow both directions. The salt bridge just reverses. But in order to do all that, we have to provide the energy now. Because everything about a rechargeable battery, when it's plugged in, it's fighting nature. It's like, I don't want to do that. You're like, well, tough. You are a 1.5 volt battery, and I've plugged you into 120. Who's going to win that battle? The 120. Now, yes, I know if you look at your things like this converter, way, way, way lowers it down. So it's really just pushing like 2.5, but still, we can use electricity to overcome this. So then it goes back there, take it out. Now it's ready to go back there. The salt bridge in a rechargeable battery is pretty much the same process. It's just wired in a different way. And it uses more efficient ones typically. A lithium-ion battery is your standard right now. When I was in high school, they were developing cadmium batteries. Those were really good, but they were really heavy compared to a lithium-ion. And so like when I was a kid, I was like 19. Yeah, I bought an 18 volt drill with a nickel cadmium battery, and it's like 3 pounds heavier than my 24 volt drill right now, which is way more powerful. And it's just all about the battery. I never know what the other half is. I should look it up someday. Every time I talk about these things in a real battery, they're way more. There's a lithium hydrogen battery. It's really way more complicated chemistry that I'm describing because I am ignoring all the other stuff besides just the two metals. Okay, here we go. This is probably just saying everything. So the anode is where oxidation occurs. The anode can be a reactant, like a metal, yada, 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 or it could be liquids in a liquid or gas phase reactant or reaction. If the anode is a metal reactant, its mass decreases. Oh, you should know that. You should definitely know that. The anode gets smaller. Now, we're not breaking any laws of conservation. The anode is a piece of magnesium, but the magnesium is being converted to Mg+2 in the solution. You okay with that? So the magnesium atom is still there. It's just not stuck to the chunk of metal anymore. It's in solution. So the mass decreases in the anode. The anode sits in an ionic solution, which allows for movement of charged particles. Electrons flow from the anode through the wire to the cathode. Anything you still writing down, or can I move forward? All right. Then everything here is the same, just opposite. And we already said all this. But at the cathode, we have red cat. Remember, reduction, cathode. All right. If the product is a solid that is deposited on the cathode, the mass of the cathode increases. Today, I only have to walk out like 5 minutes early, not 30. How hard is it to go? I'm sure he did fine.
Is everybody taking notes?
Every time that you just stop, I said stop.
Thank you.
And then I said, is anyone else taking notes? They said no. I kept going.
Well, thank you. I appreciate your studious fashion. Oh, I got it.
One of those notes. People didn't like that.
I call him Little Nelly. Or Lil Nell for short. That's his street name. What's up, Lil Nell? We all right with that so far? Okay. Here's the description of the salt bridge. Let me shrink it so it's all on the same screen. The salt bridge is a device which allows for the movement of ions between half cells. It contains an inert ionic solution. What it means by inert is that the Na and the Cl, they're not going to react with the anode or the cathode. There's no favorability in that happening. So they're just spectator ions is another way to describe them. Go ahead.
So this is just mostly a concentration gradient of charge.
100%, great way to say that. We can't ever throw that gradient out of balance. The movement of cations into the reduction half cell and anions in the oxidation cell allows charge balance to be maintained and is necessary for current to flow. If there is no salt bridge, no reaction occurs and no voltage is produced. Oh no. No, sorry, not oh no. Just one of the thorns in my side every year. Okay, so far all good. I think there's some questions coming up soon. Never mind. This is the summary, I'm sure. Hold on, let me see here. Oh, there's the one. Okay, here we go. Electrolytic cells. So you'll notice on the other ones, they have this red thing right here, right? A voltaic cell. This one is an electrolytic cell, which means I provide the power source now. In this picture, it's represented with the battery. Yes.
I was just wondering.
Oh.
The galvanic one was spontaneous, and this one.
Right. And the way you can tell in the picture, so if it doesn't name it, there's a couple ways to figure out which one you're looking at. And by the way, 90% of the time, it's what we just did. Like even more than 90%. It's almost always a voltaic cell. But if it isn't, it's an electrolytic cell, and the picture will have the battery, like it'll have a power source. All right, and this is where we make things that are thermodynamically unfavored occur because we provide the impetus. A power source is needed. The reaction often occurs in a single chamber, so there's no salt bridge. We just throw it in the same solution and connect power, and the process happens. You saw this months and months ago. The first demonstration I did was this. What did I do? I tore water apart, right? Does that sound familiar? Okay, so we look at water and it just hangs out there. Water isn't spontaneously going into H2 and O2 because that's not favored. The other way is favored, right? So water being combined in H2O is normal, but I can use electricity to pull it apart, or electrolysis, energy to tear apart. Okay, there's no salt bridge. All right, it does need to be in a solution. But so that's so that charges can flow, but it doesn't have to have a salt bridge. That's another way in the picture you could tell you were not dealing with a voltaic cell. Electrons flow from the anode to the power source and from the power source to the cathode. It occurs in an ionic solution or liquid. Cations flow to the cathode and anions flow to the anode to maintain charge balance. So these get tricky. What I would 100% do is learn the other one and then just remember this one's the opposite. So she doesn't have really any example here of what the elements are, but like I said, electrolysis is one, electroplating is one. Go ahead.
So could you say in this one, could you say that the anode is copper, the cathode is magnesium?
Yep.
Okay.
You could just switch exactly the opposite of what we just did. When they put chrome on like vehicle parts, the bumper is not all chrome. That would be so expensive. So they take, your steel, some alloy bumper, and they connect it with like it looks like a welding clamp, and electricity flows through it, and then they put it in this solution for like 5 minutes or whatever. There's math behind it that we're going to do, and then they pull it out, and suddenly it's super shiny and pretty. And we used electricity to get that to go the other direction. Go ahead.
So the only thing that switches in electrolytic cells is what we call the metals.
Mm-hmm. Which means the direction of the electron flows the unnatural way.
Battery out of water. Putting the hydrogen or oxygen part.
Yeah, and you've heard of a hydrogen fuel cell, right? It's a battery essentially where you store hydrogen, then you use oxygen from the atmosphere, react it to produce electricity to run your vehicle. And literal pure H2O comes out as the product out of your tailpipe. All right. Sound good? Okay, here's your direct comparison. So I'm not going to leave this up long enough to write every single word. So I would take a picture of it. Let me shrink it down a little. I should mark the roll, huh? You kids at Slough ever notice? Sometimes I don't mark roll till like 10:30 at night, which is 3 hours after the phone calls go out. Because what will happen, I'll get a text, and then later on I read it at night, and it was like, your son missed yada yada yada. I'm like, oh, I got to mark roll. So if he doesn't slough, then I would never mark roll. Weird. That's recording. I'll deny it though if it ever comes up.
And the thing where he says, I'll deny it.
What else did I do? I would deny denying it. Okay, here we go. Here are some questions. See if you can answer them. I'm going to pause it, make sure I joke, freaks. All right. If you just tuned in and I randomly said freaks, it's because, you know, they are. All right. When I did this, I didn't feel like rewriting all this. So here we go. The anode is the Al in the left half cell. Now listen, it's not always on the left.
But in this case, it was.
The last two it has been.
Most of the time it's on the left.
Probably.
Where?
When in doubt, choose the left. Is that where the anode is?
It's like how most of the time the most likely.
Yeah. Okay, here we go. Justify. Electrons are flowing, so it gave you the flow. So this has to be the cathode, right? Red cat, reduction at the cathode. All right, yada, yada, yada. What will happen to the mass of the zinc? Okay, well, you tell me. The mass of the zinc will increase because aqueous zinc ions are reduced, to the solid zinc metal, which is deposited on the cathode. Oh, I better send this text. If I forget this part, I'm a dead man. All right. Next, describe the motion of the ions in the salt bridge during the cell's operation. So they'll be not too bad. You can read that real quick. All right. How many went 3 for 3? Okay. If you get a question on electrochemistry, it's extremely likely you're going to label a diagram. Okay. Hopefully others also. Okay, here we go. Let me make it smaller so we're all on the same screen. Oh my, that still okay. There we go. Lots of stuff there. I'm going to pause it. No, not going to help. Not going to help. They have no hearts. Okay. Because the SN electron is losing mass at 10, I should be an adult. 10 atoms must be forming 10 ions. The process is oxidation. So which one is oxidation at? Okay, don't want that. And we're good with that? Okay. B. As the mass of 10 decreases, where does the mass go? It goes in as 10 plus 2 ions. You should, maybe you remember in the video, she said, You have to include the charges or you won't get credit. Remember her saying that sentence? So don't say that the SN just goes into solution. You should say SN goes to SN plus 2, because it's not a tin atom with all its electrons just moving. It's a tin ion. Part C, the K plus is going left and the NO3 is going right. That's all we're looking for. Does it need an explanation on there? No, but the minus is going to go towards the anode. The plus is going to go towards the cathode. Okay, and I'm going to end there. You guys have a few minutes to just chill.